All right, let's talk about the invisible rules that run everything. I mean, everything that moves, from planets spinning in space to the phone you might be holding right now. We're going to break down the absolutely brilliant and surprisingly simple laws of motion from the one and only Isaac Newton.
You know that feeling, right? One minute you're just standing there, minding your own business, and the next, the bus slams on its brakes and you're stumbling forward. It feels like some mysterious force just gave you a shove. But the answer isn't a mystery at all. It's physics, and by the time we're done here, you'll know exactly what's going on.
Okay, so before we can jump into Newton's famous laws, we got to set the stage properly. Because in the world of physics, where you are watching from can change, well, everything. To really see these laws in their pure, simple form, you need to be in a very specific kind of place.
And that special place is called an inertial frame of reference. Now, that sounds complicated, but it's not. Just think of it as any viewpoint that's either standing perfectly still or moving in a straight line at a perfectly steady speed. No accelerating, no decelerating, no turning. It's a calm, predictable stage where the rules of motion just work.
So, to put it simply, if you're standing on the ground, you're in an inertial frame. If you're on a train that's just cruising along at a constant speed, yep, that's an inertial frame too. But the second that car you're in starts to speed up, or you hop on a spinning merry-go-round, well, now you're in a non-inertial frame. And that's where things get weird, with strange phantom forces that seem to appear out of nowhere. So for today, we're going to stick to the simple, clear view from an inertial frame.
Now for what I think is the single most important tool for solving, well, pretty much any problem with forces. And don't think of it as just some boring diagram. No, this is like having a superpower. It lets you see all the invisible pushes and pulls that are happening all around us.
It's called the free body diagram, or FBD for short. And the whole idea is to take one single object, free it from everything else around it, and just draw out every single force that is acting on that object. It's an amazing way to cut through the clutter and see a problem with total clarity.
And there's a simple recipe for it. First, you isolate your object. Just draw a dot or a box representing it. Easy. Second, draw arrows pointing away from it for every single force acting on it. Third, label every single arrow. And finally, the golden rule. You have to remember this. Your final answer is only ever as good as your free body diagram. If you mess this up, the whole thing falls apart. Get this right, and you're practically home free.
So, what kind of forces are we talking about? Well, here are the usual suspects. You've got weight, which is just gravity pulling down on everything. Then there's the normal force. That's the support push you get from a surface, like the floor holding you up. You've got tension from things like ropes and cables, friction trying to stop things from sliding, and, of course, any old applied force, which is just a fancy term for a regular push or a pull.
Okay, the stage is set. We have our special viewpoint, the inertial frame. We have our secret weapon, the FBD. Now, it's time for the main event, the 3 foundational rules that basically run the entire universe of motion.
First up, we have the law of inertia. Honestly, the easiest way to think about this is that objects are kind of lazy. Seriously, they just want to keep doing whatever it is they're already doing. If something is sitting still, it wants to stay still. And if it's moving, it wants to keep moving in a perfectly straight line at the same speed forever. And there it is, the answer to our very first question. When that bus stops, your body, thanks to inertia, wants to keep right on moving forward at 30 miles an hour. That lurch isn't a force pushing you, it's just your body's own resistance to change. It's the same reason you can beat a dusty rug. You move the rug really fast, but the dust's inertia makes it stay put for a split second, and poof, it's left behind.
So if the first law is what things want to do, the second law tells us how to make them do something different. It basically says that if you want to make something accelerate, that is change its motion, you need to give it a push or a pull, an unbalanced net force. And the bigger that net force, the more it's going to accelerate.
I mean, this is something we feel every day, right? It's super easy to get an empty shopping cart moving fast. But try that with a cart that's loaded to the brim. It has more mass, so you have to push a lot harder to get the same acceleration. On the flip side, you can kick a football and send it flying, but give that same kick to a giant boulder, it's not going anywhere. More mass means less acceleration for the same force. It's all connected. And finally, we get to the famous one, the one everybody's heard of. But it's also one of the most misunderstood. This law tells us something truly profound. Forces never, ever exist by themselves. They always come in pairs. You literally cannot touch anything without it touching you back with the exact same amount of force.
Think about walking.
Your foot pushes the ground backward. That's the action. And what happens? The ground pushes your foot forward with an equal and opposite force. That's the reaction, and it's what actually makes you move. Or a gun firing. The gun pushes the bullet forward, and the bullet pushes the gun backward, causing the recoil. Now here is the absolute most important part to remember. The action and reaction forces always act on two different objects. That's the key.
Okay, let's take a breath. We have our calm playing field, the inertial frames. We have our superpower tool, the free body diagram, and we have the three big rules of the game. So, what can we do with all this? Let's try to solve a puzzle.
So, what about a situation like this? This is a classic physics setup. At first glance, it might look a little tricky, you've got multiple things going on, but if we just use the tools and rules we've learned, we can break it down into something really simple. And here's the game plan. The trick is not to look at the whole thing at once. You look at each block by itself. First, you draw a free body diagram for block number 1. Then you draw a totally separate one for block number 2. You apply Newton's laws to each diagram individually, and then you use the force that connects them, that tension in the string, to link your equations together and solve the whole thing. It's an amazing strategy that works every time.
You know, the goal here wasn't just to have you memorize some old rules from a textbook. It's about giving you a new way of seeing, a new lens to look at the world around you and understand the hidden mechanics behind, well, everything.
So let's do a super quick recap. Remember, to keep things simple, we need to be in an inertial frame. Your number one most important tool is always the free body diagram. The first law says things are lazy, they have inertia. The second law is the famous F equals ma, connecting force, mass, and acceleration. And the third law reminds us that forces are never lonely, they always come in pairs.
So I'm going to leave you with a question. The next time you're out and about, just look around. When you see a car accelerating, a bird taking off, or you just feel the chair pushing up on you, try to see the physics, see the invisible forces, the action-reaction pairs, the inertia. Now that you know the rules of the game, what new things will you see?